Now let's consider several steady flow devices and some assumptions that we have to make when it comes to considering these steady flow devices. Let's consider pipe and duct flow as our first steady flow system. In a pipe or a duct, diameter doesn't change. So if the information about the densities is not given, we can assume that the velocity change gives a negligible kinetic energy change. Also, potential energy change is going to be negligible. If the heat coming into the system and work coming into the system is not given, we can assume that they are zero. In addition, right hand side of the energy balance equation becomes zero because we are assuming steady flow and stationary system. Now our energy balance equation simplifies to this. When it comes to considering nozzles and diffusers, we have to consider the effect of velocity change. The reason is nozzles and diffusers are used for changing the velocity of the system. Generally, nozzles and diffusers are small devices, so the surface area is very small, so we can consider Q is equal to 0. In addition, W is equal to 0 because these doesn't have work coming into the system, and potential energy change of the fluid flow is going to be 0 because it's a small device, and inlet and outlet are going to be on the same level. Right hand side of the energy balance equation is going to be 0 because it's a steady state stationary system. So our energy balance simplifies to this energy balance equation. When it comes to considering turbines and compressors, turbines are used to convert mechanical energy of the fluid into shaft energy of the system. Compressors are used to convert shaft energy of a system into mechanical energy of the fluid. The theories that we are learning for turbines and compressors can be directly applied for fans and pumps. When it comes to a fan, the basic purpose is increasing the velocity of the fluid flow. So when we are solving a problem with regarding to a fan, we cannot neglect the kinetic energy change of the fluid flow. Pumps, on the other hand, mainly changes the pressure of the fluid flow. So when it comes to a pump related problem, if the inlet diameter and outlet diameter is not given, you can assume that the kinetic energy change of the fluid flow is negligible. So when you are analyzing a compressor, for an example, you can assume that the heat losses from the compressor is negligible. Generally, compressors and turbines are insulated. So if the question does not give you the heat loss, you can assume it to be 0. However, for a compressor or for a turbine, W is not going to be equal to 0. If you are using the formal sign convention, work came into the system is negative. So for a compressor, since the work is coming into the system, we have to consider that the work came into the system is negative value. If velocity change is not mentioned in the question, you can assume that the effect from velocity change on the energy of the fluid flow is negligible, and you can neglect that v squared over 2 part of the energy balance equation. And the right hand side of the equation is going to be 0 because it's a stationary and steady system. So our energy balance for a compressor is going to be something similar to this. When it comes to a turbine, the only difference is work is going out of the system. As I mentioned before, if your system is a fan, you have work coming in. Most of the time you can neglect the heat losses from a fan because it's not going to be significant. However, kinetic energy change of the fluid flow should not be neglected because the main purpose of a fan is changing the kinetic energy of the fluid flow. A throttling valve is a device that we use to reduce the pressure of a fluid flow. So this throttling valve can be a porous plug, it can be a disc with a hole in it, it can be an adjustable valve, it can be any sort of a flow restriction device. Since these throttling valves are very small, the Q came into or went out of the system can be neglected. There are no work coming into the system, and potential energy change of the fluid flow is neglected. Since this is same diameter at the inlet and outlet, we can neglect the kinetic energy change of the fluid flow. Right hand side of the equation becomes 0 again. So for a throttling valve, energy balance can be simplified to say that H1 is equal to H2. Since enthalpy is defined as internal energy plus PV, we can rewrite this energy balance in the form of U1 plus P1 V1 is equal to U2 plus P2 V2. When it comes to a mixing device mixes fluids at two different temperatures and gets a mixture of fluids which is at an intermediate temperature. Again, mixing devices are considered as small devices, so heat loss or heat gain through the system boundary can be neglected, work came into the system can be neglected, potential energy change of the fluid flow can be neglected, and the velocity changes are generally neglected if the diameters of the inlet and outlet is not given. However, one crucial thing to understand here is that mass comes into the system from two inlets and mass goes out of the system from one inlet. So it is necessary to write a mass balance equation for a mixing device. So you can show your final energy balance equation in this form for a mixing device. In a heat exchanger, there are two major parts, the tube section and the shell section. Let's assume that the streams coming in and out of our heat exchanger is 1, 2, 3, 4. And let's try to analyze these parts separately, tube part and shell part. And we can consider the entire heat exchanger as a single system. When we are writing the energy balance equation for the tube section, let's assume that tube carries hot liquid. So Q goes out, negative Q, no work coming in, and we have one fluid stream coming in and one fluid stream going out. We are assuming that the potential and kinetic energy changes of the fluid stream is negligible, stationary and steady conditions. When we are considering the shell section, the heat lost from the tube is gained by this shell section, so Q becomes positive, and we have one fluid stream coming in and one fluid stream going out. That is equal to 0 because steady and stationary. When we are considering the total system, we can assume that Q lost from the system is 0, assuming it's adiabatic, and we have two fluid streams coming in and two fluid streams going out of the system. So if the question gave us a heat loss from the heat exchanger, we have to consider it here. And then we can write the mass balancers. M1 is equal to M2 because it's a single inlet and single outlet system, and we can call it as M hot. And M3 and M4 can be equal to M cool. And we can write the mass balance equation for the entire system as M1 plus M2 is equal to M3 plus M4. And all of the masses in this analysis should be M dots because we are considering the rates of fluid streams.